Welcome back to the Deep Dive,
It's great to be back.
where we delve into the intricate world of mathematics.
Exactly.
And for our number theory enthusiasts joining our OEIS exploration,
OEIS. Yeah.
today we're taking on sequence A00187,
Right.
generalized Euler numbers.
Yes.
And the OEIS, is just this amazing treasure trove of numerical patterns.
Absolutely.
And the generalized Euler numbers are such an elegant example of how these mathematical concepts are just so beautifully interconnected. They build upon the classical Eulerian numbers and kind of offer a wider view of some of these combinatorial structures.
Yeah.
So our goal today is to really just give a nice, concise introduction to these numbers,
Right.
drawing from some of the research that's been done and just highlight what makes them so fascinating.
Yeah, definitely.
So, for those who might be familiar with the standard Eulerian numbers, they basically count the number of permutations of nominal elements that have exactly dollar cents.
All right.
When we talk about generalized Euler numbers, what exactly are we generalizing here? What's like the core idea that we need to grasp from the very beginning?
Well, at its heart, the generalization extends the way that we actually count these ascent-like patterns.
Okay.
So the generalized Eulerian number denoted by 1 equal 1 for 0kn on Euler can be defined explicitly by this formula, banana k1, j, lmk, adre, and a.
Yeah.
Now, this formula might seem a bit abstract at first, but think of it as a way to use the principle of inclusion-exclusion
Okay.
to precisely count these permutations with a specific number of ascents. So the alternating sum and the binomial coefficients, they work together to actually filter out those permutations that don't meet the exact criteria for ascents.
Oh, that's helpful.
Yeah.
So that formula gives us a direct way to calculate these generalized numbers.
Yeah.
Now, I understand that Euler himself had a way of looking at these numbers through generating functions.
Yes, he did.
What did his approach reveal?
Right. So Euler, as you know, was a master of generating functions.
Yeah.
And he provided an early way to represent and study these numbers through this expression.
Okay.
Frac g plus FCM meta plus 1HNX frac g, along with the relation sex by 1a plus 1AN ANX tan 1.
Got it.
Now, while the first part of this generating function is a bit involved and requires more context on nulli s, x, br, x, and a t day,
Right.
the second part is more directly relevant to us.
Okay.
It shows that the generalized Eulerian numbers, S, B, R, K, appear as the coefficients of powers of $6 in a polynomial that's related to 1x mani.
Okay.
And generating functions basically package a whole sequence of numbers, like in this case, 1n for a fixed dollar into one single function.
Got it.
So it makes it easier to manipulate and extract properties.
So Euler used these generating functions to understand these numbers better.
Right.
Has the way we represent them evolved since then?
Yes, it has.
Is there a more modern, maybe a more accessible form?
Yes, there is a more contemporary generating function that is widely used today, and it offers a very compact and powerful way to actually encode all of the generalized Eulerian numbers.
Okay.
And it's given by this: ln 1 plus sum k reno n k1.
Yeah.
This form is quite elegant because it relates these generalized Eulerian numbers to the exponential function, which is a very fundamental building block in many areas of math.
Right.
And you can actually see how these coefficients, in 1n and k, are naturally embedded within this structure.
It does look pretty powerful.
Yeah.
Now, one of the key benefits of having a generating function is often the ability to derive relationships between terms in the sequence.
Exactly.
Does this modern generating function help us find a recurrence relation for one earned card dollar?
Absolutely. From this generating function, we can derive a crucial recurrence relation that tells us how to calculate 1n plus 1k based on the values of a ln plus 1nk based on the values of the previous level, no nk. This relation is 1n plus 1k plus 2 and nk1 plus k and nk. And recurrence relations are incredibly valuable because they provide a step-by-step method for computing these terms of the sequence, often revealing these underlying patterns.
Right.
And as the source notes, this particular recurrence can be derived from the generating function through some careful manipulation of the series.
So recurrence relations give us this computational handle on these numbers.
Exactly.
Now, the name Eulerian numbers itself kind of suggests a connection to permutations and their properties like ascents.
Yeah.
Do these generalized numbers retain any of those symmetries that we see in the classical Eulerian numbers?
Yes, they do. Just like the standard Eulerian numbers, the generalized Eulerian numbers exhibit a beautiful symmetry.
Okay.
$NK with, say, n NK plus 1 day.
Hmm.
Think about a permutation of knot elements.
Okay.
If it has $ascents,
Right.
what happens if we read it in reverse order?
Yeah.
Each ascent becomes a descent, and each descent becomes an ascent.
Okay.
So a permutation with the $ascents read in reverse.
Mm-hmm.
We'll have 1K plus 1, well, plus 1 involves NK ascents.
I see.
So this fundamental symmetry in the structure of permutations directly translates to the symmetry we observe in the counts given by the Eulerian numbers, both classical and generalized.
It's a very intuitive way to see that symmetry.
Yeah.
Now, our sources also introduce something called limiting Eulerian numbers, denoted by CERN, KRN.
Okay.
The term limiting suggests we're taking some sort of limit.
Yeah.
What parameter is approaching a limit here?
Okay.
And what are these TRN, KR numbers all about?
Well, this is where the generalization takes another interesting turn.
Okay.
We introduce this parameter, $3,
Right.
and we define the limiting Eulerian number of order 2Rn, TRN, through this generating function,
Okay.
R1x RO, where CRRx, 1 plus x plus by 2 plus dots plus xr1 x day r, and math for x dir, and 9x 10 federal 1. And math for x is a differential operator that scales with $6, often appearing in these contexts involving generating functions and combinatorial identities.
Okay.
The parameter dollar essentially introduces a level to our generalization.
That looks significantly more complex than what we've seen so far.
Yeah, it can get a little bit intricate.
What's the payoff for introducing this dollars in this more intricate generating function? How do these Tiergully dollar relate back to the standard Eulerian numbers, the large dollar that we started with?
Well, the fascinating connection is that these limiting Eulerian numbers, $, are directly linked to the standard Eulerian numbers, not the generalized ones we first defined as Euler.
Right.
And the relationship is given by this. 2RLN metal 1K plus 1 AN 1K T. So these CRM KT are essentially signed versions of the standard Eulerian numbers.
I see.
Where the parameter in dollars is 901,
Right.
with a sign that alternates with dollar.
Got it.
This shows a deeper connection between these seemingly different generalizations of the original Eulerian concept.
So the TRNK are tied to the standard Eulerian numbers.
That's right.
Now, our outline mentions a polynomial GRN, x, x in k wiggy, xta, xkk.
Yes.
What are some key properties of this polynomial?
Okay.
Why is it useful to define this polynomial based on these TRNK coefficients?
Well, DRnx is a polynomial with some very interesting characteristics.
Right.
First, its coefficients. The TRnk values are always integers.
Yeah.
Second, the degree of this polynomial depends on nominal and dollars. For 1, the degree is 3r, while for 1 the degree becomes nominal and aller. We also know the values of the first and last coefficients. TRN, eider to me. And for 1 dollars, nominal and per 1.
Okay.
By packaging these TRN and K values into a polynomial, we can leverage the powerful tools of polynomial algebra and analysis to study their properties.
Polynomials often have recurrence relations that govern them.
Yeah.
Does DRnx also satisfy such a relation?
Yes, it does. The polynomial DRn follows this recurrence. GRN plus 1x, xnryr, GRN x xn, GRN xn, where GRN denote the derivatives with respect to $6.
Okay.
This recurrence allows us to generate these polynomials iteratively, building up from lower values of dollars.
Got it.
And it highlights how the structure of GRN at one level is related to its derivative and the function at the next level.
We discussed the symmetry of WAN-N.
Yes.
Do the limiting Eulerian numbers TRN and K also exhibit any form of symmetry?
Yes, they do have a symmetry property, although it involves the parameter dollar.
Right.
The symmetry is given by CRNK, or NC1N, KRN in RK.
Got it.
This tells us that the coefficients of the polynomial GRN x are related in a very specific way, with a possible sign change depending on dollar between terms that are equidistant from the beginning and the end.
The outline also points out some interesting values of GRN and SCRN.
Oh, yeah.
We evaluate it at $6 and $6 and a tandem on 1 artlight. What do these values tell us?
Okay, so evaluating GRN at these specific points reveals connections to other fundamental mathematical constants.
Oh, wow.
For sexagulls, we find that GRN 1 mile hen and actually psycho 1 and act 1 and act 1 iron ash plus 1 nr plus 1 n1 frac b n 1 where bother dollars is the Bernoulli number.
Wow.
This is a striking link between these generalized Eulerian numbers and the Bernoulli numbers, which appear in a wide range of mathematical areas, including number theory analysis and even physics.
That's quite a connection.
It is.
Now, what about when we set sexagals E-1 L1?
So the value of GRN1-1, ADIsh1, and ASH1, MyAsh1, it depends on the parity of $2.
Oh.
If 2 is odd, we have the relatively simple result, GRN plus 1, Ninish 1.
Got it.
However, if 2 adheres is even polarizing, the situation is a bit more involved.
Oh.
In this case, GRN minus 1 equals odd is odd.
Right.
But if 2 is even, it can be expressed in terms of Bernoulli numbers again, although the formula is much more intricate. Our source even provides some specific examples. She for certain all race matters, unanage 1, nickels 78 uncles and netters, nanagers and 9 edges and antifators and netterators and 3, noting that these can be verified using a specific theorem within the source material.
Okay.
These evaluations at 6 0 initial Lun often relate to alternating sums of these coefficients and can reveal some deeper structural properties.
It's remarkable how these numbers connect to factorials and Bernoulli numbers. Now, the next step in our exploration is considering this limiting case where 2 approaches infinity.
Right.
What happens to 2 Eulerian k in this limit?
So as 2 array tends to infinity, the limiting Eulerian numbers Eulerian k converge to values that we denote as Eulerian.
Okay.
This creates an infinite triangular matrix of these Eulerian k numbers.
Right.
The generating function for summed array k SKO in this limiting scenario is given by GON x CON 1 XKO in this limiting scenario is given by dic 1 x BRN x KO and double ket natter, some K1 x and KO.
Yeah.
And interestingly, in this limit, the numbers CRN k turn out to be positive integers, which is a significant shift from the signed TRN KO.
So by taking this limit,
Yes.
we arrive at a new set of positive integer sequences.
Exactly.
Do we have a way to directly calculate these triniteger values?
Yes, there is an inversion formula that allows us to express some tapenomon binamatic manum and keme. While it involves these binomial coefficients with negative entries, it provides a direct way to actually compute Tirena without relying on that limiting process.
And how do these Tudinin K and Dairy relate back to the original generalized Eulerian numbers, Dinana, that we started with? It seems we've branched out quite a bit.
Yeah, well, the connection perhaps surprisingly comes through their generating function. We have this relationship, summa k and ken and xk, summa k1 fen and 1k and x.
Right.
This shows that the generating function for the limiting Eulerian numbers, summa k and is related to the generating function for the standard Eulerian numbers with parameter n and Hel1 dairy by a simple factor of fer 101 and dairy. This highlights this web of interconnectedness between these different types of Eulerian numbers.
Recurrence relations have been a recurring theme throughout our discussion.
They have.
Do the T-sum K numbers also satisfy any such relations?
Yes, they do. There are a couple of important recurrences for T-sum K.
Okay.
One involves the Stirling numbers of the second kind, ZSN, JSN, which count the number of ways to partition a set of any elements into DS non-empty subsets.
Okay.
2 sum K plus 1K. KSNJ. Another recurrence relates T-larva at level $1 to values at level 1 NCN plus 1 emitin plus 1 ketalarva NMGN.
Got it.
These recurrences provide different ways to compute and understand the relationships between these limiting Eulerian numbers.
The outline then introduces the difference operator, delta FK, FK1.
Right.
What role does this operator play in the study of T-sum K?
Applying this difference operator repeatedly to T-sub reveals a fascinating property. Theorem 10 states that deltans CF5 T1 for $1 is K loan and 0 Visas in dollars. This connects the limiting Eulerian numbers to powers of Kähler through the concept of finite differences.
Okay.
It shows that the nutha difference of the sequence TMFN essentially recovers a simple power function within a certain range.
Finally, the outline mentions sinister diagonals. That sounds like a very specific term.
It is.
What are we referring to here in the context of the CNK matrix?
So if we arrange the CNNK values in an infinite matrix where nothing indexes the rows, starting from $1 and Tenia indexes the columns, starting from 12 and 1.
Got it.
The nantha sinister diagonal consists of the elements CNN plus 1K for Kels ranging from $1 to non-dollar. For example, for $1 to 7 Charles, we get the sequence $1, 38, 176, 272, 182, 56, 71.
Right.
Which sums to $738 or $2. Theorem 12 provides a generating function for these diagonal elements. CNN plus 1K XK X1 plus XN1.
Okay.
This gives us a compact way to represent and study the sequences formed by these diagonals.
And our sources also hint at the existence of congruences for these numbers.
Yes.
That suggests they have deeper connections within number theory.
Yes. The Brandeis source mentions that congruences do exist. for these generalized Euler numbers, indicating that they exhibit this predictable behavior under modular arithmetic.
Interesting.
This points toward connections with these deeper number theoretic structures and properties.
Right.
For instance, there is a mention of a congruence dollar equipped to P mod.
Okay.
Where lie is a prime, and Euler is related to these numbers, along with a specific example. $24.33, Flash 2047, other Lars Edinburgh Enter 27, $35 and half 5 hours. These congruences open up avenues for further exploration into the number-theoretic nature of these sequences.
Well, this has been a comprehensive journey through the landscape of generalized Euler numbers.
It has.
Touching on their definitions, various generating functions, recurrence relations, symmetry properties, the relationship to standard Eulerian numbers, the fascinating limiting case, and even a glimpse into their number-theoretic properties through congruences.
Exactly.
It's clear that what starts as a generalization leads to this really rich and interconnected set of mathematical objects.
It does, absolutely. These numbers appear in diverse areas of combinatorics and number theory. And the relationships we've explored today underscore their significance. The transition from the initial generalization 1nk to the limiting case ascent k reveals this beautiful hierarchy of sequences with their own unique properties and connections back to fundamental mathematical concepts.
So for our listener, particularly those number theory students following our OEIS explorations, what's a key takeaway or maybe a provocative question to keep in mind regarding these generalized Euler numbers?
Perhaps it's this. We've seen how the classical Eulerian numbers connect to the ascent patterns in permutations. How might these generalized forms, both EMKAT, and their limiting behavior in ascent K relate to more complex combinatorial structures or perhaps different types of orderings or patterns?
That's a good question.
What new combinatorial insights might these numbers reveal if we can fully unlock their combinatorial interpretations? I encourage you to delve deeper into the OEIS, explore the referenced literature, and see if you can uncover some of these hidden combinatorial meanings.
Excellent food for thought. Thank you for sharing your expertise with us today.
It's been a pleasure.
Until our next deep dive, keep exploring the fascinating world of mathematics.
Absolutely.
See ya.